Hello and welcome back to 6034 Fall 2020 edition. Today is the fifth installment of these recorded recitations. Today we're going to be talking about Bayes nets. This will be the first of a series of 2 recitations on Bayes nets. Today in particular we're going to cover, let me pull out the schedule, we're going to do a probability crash course for those of us in the class who don't have a formal probability background. And then we'll go over the very basics, or the very beginnings of what we cover as far as Bayes nets and Bayesian inference within 6034. Those of you who are familiar with the axioms of probability and have taken a probability course before would likely be better served taking the first part of this recitation as a light review. If not, just skip ahead to the second half where I begin to talk about Bayes nets and where we perform, I'll just bring up the schedule, I explain the naive Bayes assumption, I go through an example of d-separation, and one of explaining away, which are the important concepts within 6034. Right, so let's get started first with a pictorial example of probability, and this is for those of us who don't have as much a strong probability background. And I want to make it the classic coin flipping example. And in a world where coin flipping is everything, and it's only one coin flip, let me start writing that down. My entire universe is one coin flip. And so my universe consists of this coin flip, so it either is heads or tails. And I know many of you are jumping already to the fact that, okay, so 50-50 more or less, but I want to get into the subtleties and definitions via this coin flipping example. So I want to define my universe as omega. So omega is the space of all possibilities or all things that can happen within my universe. And within my universe, all these things that can happen are called events. And in this universe in particular, I have 2 events. I have the event that I have a heads and the event that I have a tails if my universe is only one coin flip. And in order to talk about these events more easily and to start defining our probabilities, we define variables as well. So let me define the variable A, and A is going to be the result of flipping a coin. So A in this universe is either H or T for heads or for tails, which means now I can talk about events in terms of variables. An event then, in this case, in this framework and in this example, an event is when a variable takes on a defined value. So my variable A in this side of the universe takes on the value H, and on this side of the universe, it takes on the value T. And as you probably already guessed, the probability of A equaling H, of that, which means the probability of that event happening, is equal to either 1/2 or 0.5, depending on how you look at it. And the other way is also true, the other event. And one way you could start thinking about this is I tried to, as closely as possible, split the larger rectangle into half. So in this universe, half of the space of my universe is occupied by one event, and the other half is occupied by the other event. So you can, if you think about it geometrically, and that's part of the reason why I use these geometrical figures, half of the area of the black outer rectangle is occupied by the yellow square or the yellow rectangle, and then half the area is occupied by the blue rectangle. So you can think of the probability of this event happening as the fraction of the area, or the area of the yellow rectangle divided by the area of the larger black rectangle. That's another way of thinking about it. but we'll go more into detail with after the formal definition. So I want to write out explicitly what these variables and events are. Variables are precisely as the name implies, just variables. I can define any letter to be a variable. And then I have events. Those with probability background, you know that I'm glossing over different random variables, Bernoulli indicator random variables, etc. But we just want to keep the basics of probability just enough to understand Bayes nets. So events are then when variables take on a value. And so that can take on many forms. So let's say a equals a, or lowercase a, and by that I mean lowercase a being any number. Because in the previous example, I was using coin flips, heads or tails, but a could be, I don't know, the number of droplets that fell into a glass of water during rainfall. So in 6034, at the very least, we refer to these as discrete. I'll leave it with an asterisk because this is a simplifying assumption that we make. We won't be dealing with continuous random variables or continuous probability spaces in this recitation. Okay, so a is either 1 or 2 or 3 or -1 or -100. Then a is equal to either true or false. That's another possibility. This is one way we can abbreviate them. And in this case, a is a Boolean variable. For the purposes of simplicity, I'll be carrying over the coin example throughout this recitation and these concepts. So I'll mostly be dealing with either a is equal to heads or a is equal to tails, a equals h or a equals t. Okay, so now let's complicate things a little bit. Let's say my universe is not one coin flip, it's two, and they're in order. So first let me define a new variable. I had said earlier that a is a result of a coin flip, but let me just say that a is the result of the first coin flip. Because my universe is now two coin flips. And now I'm going to define b. b is the result of the second coin flip. And this is a fair coin, just a standard quarter if you want to take one out of your pocket. So there's nothing funny happening here, which means heads or tails is 50-50. And I have, it may be a little bit harder to see now that there's more junk in the rectangle, but I still have the yellow inner rectangle here and the blue inner rectangle here. So I'm gonna carry over from the first diagram the event that a equals heads or a equals tails, right? Because the first flip can only result in either heads or tails. That is not going to change. But then I have b, the second flip, and the second flip can again only be heads or tails. And now we start getting into, now that we have this space defined, I want to start getting into the types of probability that you're going to encounter. So my universe is no longer a single coin flip. Correct? My universe is 2 coin flips, which means a fully defined event in my universe is 2 coin flips, meaning either heads heads, heads tails, tails heads, or tails tails. But earlier when I was drawing in the A equals heads, A equals tails, I said, well, the first flip can only either be heads or tails. So I can still talk about the probability of A being heads or A being tails anyway. So there has to be some sort of distinction. And this is where I start introducing terms. So I mentioned a well-defined event. And in my universe, at least, a well-defined event is one where, because it's 2 variables, 2 coin flips, A takes on some value and B takes on another value. They can be the same value or they can be different values. Because this means that I've performed in this P, the probability of A equal X and B equaling Y, that's just 2 flips. And that's what I call my joint probability, because it's an event that includes all the variables within my universe. But, as I mentioned earlier, I can still talk about the probability of A equaling X, or I can talk about the probability of B equaling Y. And the reason for that is I'll do some rough highlighting here. Let's say I want to talk about the probability of B equaling Y. Then I can start to focus on this area here. B is this long rectangle that's crossing the space, if Y equals T. So I'm focusing on that area, so I can still talk about it. In this case, the probability of B equaling tails is 50, heads 50. And this is what we call a marginal probability. It's one where we get the probability of an event that does not include all the variables, where not all the variables in the universe take on a specific value. So in this case, it's as if I had said the probability that A equals anything, but B equals tails, in this what I've highlighted in black. And let's define it formally now. There's a lot of writing in this and in these slides, so in order to not have the whole hour be me talking into the mic as I write slowly, I've written out some parts and I'll be filling in the equations myself. So the joint probability, as I mentioned before, is a probability of an event where all the variables in the universe take on a defined value. And in this example, I'm now using a universe of 3 variables. The joint probability looks like this. The probability that A equals some value, B equals some other value, and C equals another value. And then we have the marginal, where not all the variables take a defined value. And an example of this is A equaling, in my universe of 3 variables, A equals A, B equals B. C can equal anything. Or, alternatively, I could say C equals C, or I can even say just A equals A. Those are marginal probabilities. And now it's important to have a tool to go from one to the other, from a joint probability to a marginal one. And even though it might be a first instinct and to think about the coin flipping example, oh, I just think about the second coin flip and not the first one, and that's easy, 50-50. There's an assumption there that we will talk about later, which is why it makes it so easy. So I want to make this formal. The probability of A equaling A in a universe where A, B, and C are my variables is the same as 2 sums, a double summation. So I want to sum all the events where the probability where all the events where A equals A, B equals some value, and C equals some value. And what's happening in this equation is I'm going through all possible values of B, all possible values of C, and I'm taking the probabilities of all those events, but maintaining A equals A constant, my event of interest, and I'm summing over all of those. So you can think of it as, in the coin flipping example, I listed earlier the 4 combinations that I could have. I'll write it in red because it's example. Oops. I'll write it to the side too. I can have either heads heads, heads tails, tails heads, or tails tails. And I'm interested only in when the second flip equals heads, as an example. So I have to sum, in this case, 2 events. This one and this one. So I've summed over all the possible values of A because I'm not interested in A, and I'm just interested in the probability of B equaling tails, assuming this is A and this is B. A simple example, but it's meant to just cement the concept of the equation a little bit further. Okay. Now I'll read you the diagram, but this time I want to introduce yet another and one last type of probability. So as I had mentioned before, this is region, or this large long rectangle. B equals H, heads, B equals tails, A equals heads, A equals tails. And A is still the first flip, B is still the second flip. And now I want to think, one thing that we did in the previous slide was sum over all the possible values of A. And so I want to jump on that concept just briefly. So let's say I assume that the second flip is heads. And I'm interested in some probability within the universe where the second flip is heads. So in reality, I'm taking this omega, this universe, and I'm zooming in to a section of it. So suddenly, when I say the probability of A equaling something, I'm not going to define it yet, given that B, the second flip, equals heads, this is a new universe. This is now my universe or my area of interest. So now that I'm zooming in on this B equals H area, I want to ask myself, let's say I now say, what is the probability of A equals H in this area? Well, A equals H, thankfully, where A equals heads, occupies exactly half of the area. Which means A equaling heads, given, or the first flip being heads, given that the second flip is heads, it's just 1/2. But the reason we got 1/2 was because we forgot the old universe where we had 4 quadrants, and then we went to a new universe where we only had 2 quadrants, as in the very beginning of Recitation, where in the beginning I only had A equals heads, A equals tails, and nothing else. So now within B, I have A equals heads, A equals tails, and nothing else. And then I just had heads. Okay, so a brief recap. I'm just going to write the equations so that you see them all together. And we're back into a universe of 3 variables here. The probability of A equaling A, some value, B equaling some other value B, C equaling C. Then the marginal is the probability of an incomplete set of variables. So I'll just repeat the equation from earlier, where we sum over all possible values of B and C. Maintaining a constant. And now the conditional one, formally said, is given an assumption, or given that some event happened, what is the likelihood of another? And the way we define it is in 2 variables, the probability that A equals A, given, in this case, what I'm assuming to be true is that B equals B, and that C equals C. I could have defined it differently. I could have said that what is the probability that A equals A and B equals B, given, as in moving the vertical bar one to the right, given that C equals C. I could have switched A and C. I could have written it in many different ways. It's just that to the right is something that we are assuming to be true, and to the left is what we are looking for in the new universe that we defined to the right of the vertical bar. And again, in the previous slide, I gave you an equation to go from joint to marginal probability, and now I want to give you an equation that combines all 3. So how do you get the probability that A equals A given some event, in this case B equals B and C equals C? Well, I need the joint probability of all of them. The probability that A equals A and B equals B and C equals C. And I divide it by the marginal probability of the event that is where I'm conditioning. And I want you to stare at it and think to yourself, does this make sense? And this is where the geometry analogy that I mentioned briefly in the first slide comes in handy. So I'm looking at here, if we think back to the coin flipping example, let's go back to the coin flipping example. If I'm interested in the joint probability, I'm interested in the event A equals heads and B equals heads. And I'm going to divide it by the marginal, which is the probability that B equals heads, because my conditioning is on B equals heads. So what's happening really? So I'm taking the area of this smaller yellow region, and I'm dividing it by the area of the B equals H rectangle. So it's very, very similar to what was happening in the first slide, where I was dividing the area of half the universe by the entire universe. So now the division is happening between the area of whatever's on the right of the conditioning bar in the denominator and whatever's to the left of the conditioning bar in the numerator. And more explicitly, this is a division between the joint probability divided by the marginal probability. Okay. Now finally, I'm going to rewrite the conditional probability, and I'm going to derive a very important principle that we're going to use in 6034 for Bayes nets, called the chain rule. So just rewriting what I mentioned earlier, or not earlier, literally in the previous slide. equals the joint probability divided by the marginal. Okay. And I just want to work through the equation a little bit. I'm just going to move the terms left and right. It is an equation, so this is a perfectly valid operation. So what I'm going to do is I'm going to take this term and I'm going to write it on the left-hand side. Probability of A equals A, B equals B, C equals C, equals, and in order to get it by itself, I need to multiply by the marginal probability on both sides. So I have the probability of A equaling A given B equals B, C equals C, times the probability of B equals B and C equals C. So in this case, I'm multiplying, when I multiply the conditional probability by the marginal probability of the event on which I am conditioning, I get the joint probability again. And if that rule holds, then I can apply it again, because I have an event defining B, I'm conditioning on B equals B and C equals C, so I can probably condition it further, or I can split it up further as follows. A equals A, B equals B, C equals C. Probability of A equals A. The given stays the same because I conditioned on that event. But now things start getting interesting because I can split this. I just said the joint is equal to the conditional probability multiplied by the probability of the event on which we conditioned. So I can rewrite this marginal the same way. I can rewrite it as the conditional probability, the probability of B equaling B, given that C equals C, multiplied by the probability of the event on which I am conditioning. And that is the chain rule. And an equivalent way of saying it, or writing it, because I can split it up multiple ways, is the same term as above. The probability of C equals C, given that A equals A and B equals B, times the probability of A equals A, given that B equals B, times the probability that B equals B. This is also an equivalent way of writing it. And I can split it up in different orders as long as I am consistent in what I condition on a variable or on an event, and then I multiply by the probability of that event later, and then I can split that other event further. Okay, so that was a lot, so I just left the equation there, and I want to use this chain rule to derive Bayes' rule, which is going to be the bread and butter of this. Not particularly this recitation, is going to be mainly probability review, but the topics that and the exercises that we'll be performing in 6034. So what I've done here, and I got a little bit ahead of myself, is I redefined the universe to just A and B because I wanted to make it a little bit simpler. And I have the chain rule here in terms of just two variables. A and B is the conditional times the marginal. Again, the conditional times the marginal. And what I did is these are two equivalent ways of writing it. You saw it in the previous slide. I could break it up in different ways. So I just set them equal to each other because they're equivalent. The probability of A equals A condition on B equals B, and then times P, the probability of B equals B, and it's equal to splitting it the other way around. And to get Bayes' equation, it's just one more step. And I'm just going to divide by B equals B. Probability that A equals A, given that B equals B, is equal to the probability that B equals B, given A equals A, times the probability that A equals A, divided by the probability that B equals B. And that is Bayes' rule. It is you can derive it directly from the chain rule, and this is a very, very powerful equation. Well, I won't say very, very much about it at this point because we won't be using it in this recitation. I introduce it now because I want to, let me just flip back so that you can take a look at it for 30 more seconds. I introduce it now because obviously this recitation is Bayes part 1, but when we'll be using it is in the following recitation. And it's a very keystone equation in terms of Bayesian inference and a lot of machine learning and artificial intelligence as a whole, just to end up throwing all the buzzwords in my pocket. But moving on. Now that we're exhausted with probability, I can talk about exhaustion. And no, it's not actually in that sense. This is, for those of you familiar with probability, this is akin to the second axiom of probability. So if I have some event, or some universe, and it has a slew of events in it, if I take the probability of each individual event in my entire omega space, and I sum all of those probabilities, I will always get 1.0. That is invariant. So the sum of the probabilities of all the probabilities in the universe is equal to 1. Or the probabilities of all the events that define a universe is equal to 1. So I said this is akin, not exactly, but very close to the second axiom of probability. For those of you curious to learn more, you can feel free to look up the 3 axioms of probability, and you can keep reading from there for your personal enrichment in this area. Okay, so a few examples of how this works. Let's say in my universe I only have one variable, A, so all the events in my universe, and if A were Boolean, would be A equals true and A equals false. So now I'm summing over all the events in my universe, and I know this has to be equal to 1.0. Boolean, not Boolean. Okay, so what if I move to discrete? Oops. The probability that A equals some value plus the probability that A equals some other value plus ... Let's say I sum over all the possible values of A. A can go from 1 to 100, or some number n. It can go up to A can take n different values. Then when I sum through all of them, I will also get 1.0. And if you remember, when we were doing conditional probability, I put it in terms of forgetting the old universe and now taking a look at this, or zooming in to this new universe. So in conditional, it also applies. And now my universe in this case, or I'm going to say the parent universe, I'm pretty soon going to start talking about the multiverse. In my parent universe, I have two variables. So let's say I am conditioning on one event, that b equals b1, or it can be any one. It can be b7 for all intents and purposes. So I conditioned on b7. So the event, or how shall I say it? All the events where b equals b7 are the new universe. So I have to sum over a equals a2 given that b equals b7. And I do that just the same as I did in the line above, all the way up to p of the probability that a equals an, but maintaining b equals b7 constant, because I'm summing over the events in that universe where the event b equals b7 is true. And this is also going to be 1.0. I'm not going to use a diagram to further illustrate this one, because it's been many diagrams and there are more coming, just like this one. So, pardon my allergies. Where was I? Okay, so now we're going to talk about independence. And let's redefine or repeat what we said earlier. We're back to the coin flipping example. We're back to the universe where we're only dealing with two variables and four possible events. A is the result of the first coin flip, B is the result of the second one, and both A and B can either be heads or tails. So B equals heads, B equals tails, A equals heads, A equals tails. Now let's think back, and I briefly mentioned it a couple times, but I think I want to make explicit note of this. So when we were thinking, what is the probability, and I said it, I gave it away the first time I brought this example up. You're thinking, what is the probability that the first flip is heads? And we thought, or I said, the second flip can be anything it wants, but it's not going to change the first one. It's either going to be heads or tails, no matter what. So in the case that B equals tails, the probability that A is going to equal heads is the same. And one way of writing it is the probability of A, we just clarified it's 1/2. But let's say, let me make the amendment here that A equals heads. Tails is the same thing, as in it's also 1/2. But what's the probability that A equals heads given that the second flip is tails? So let's do the exercise one last time. So now I'm looking at this area, the bottom area, the shaded area, because I'm conditioning on that event. That's my new universe. And half of that universe is occupied by the event A equals heads. So it's still 1/2. Which means the probability of A equaling heads is the same as the probability of A equaling heads given, I'm going to abbreviate due to lack of space, the event I defined above, B equals tails. And that is the definition of independence. More explicitly, as we've been doing, A and B are independent, and this is the abbreviation for A and B are independent if and only if. This is a lot to write, so I'll be abbreviating it as if double F. The probability of A equaling some event. Pretty soon I'll stop writing A equals A and I'll just write probability of A. But just know implicitly that I'm assigning a value to A and to B. The probability of A equaling A given that B equals B is equal to the probability of A equals A. And the way you think about it is two variables are independent when one taking on a value does not give you information about the other one or the values that the other one will take. And I'll show you, let's say we're not talking about coin flips. We're talking about, let's say it's only one coin flip, but I still have two variables. One is the result of the flip, and the other one is whether the coin has two heads or is a normal coin. Those variables are not independent because if you have knowledge of the coin being either fair or having two heads, then that informs you of the probability of the first flip being heads or the first flip being tails. And the other way around too. If you get tails, you automatically know that the coin is not the one that has two heads. So you get information from the values that result from two variables, so they're not independent. A direct consequence of independence is that the probability of A and B, and this is where I start abbreviating, but reminder that this is the probability that A equals A and B equals B, is equal to the probability of A given B times the probability of B. This is an application of the chain rule discussed earlier. And then, because this is equal to the probability of A, this is the same as the probability of A times the probability of B. And this is going to be, this implication is going to be very, very key in a later concept. So now, yet another diagram, because we're going to talk about a conditional independence, which I found harder to grasp than standard marginal independence, and I want to give it, in this case, I really do want to make sure the example is clear. So standard example, P equals heads, A equals heads, whoops, A equals tails, and B equals tails. And I've defined a third variable, C. So this variable is, let's say it's Boolean. It takes either true or false. And when it's true, I know that it's only two flips, my universe. So when C is true, I know it's either heads and then tails or tails and then heads, but not both tails or both heads. That's what C tells me. Let's assume I have no knowledge of C. It's a value in my universe, or a variable in my universe, but I have no knowledge of it. Then the probability of A and B, they're still independent. As in the previous example, as if C didn't exist. But let's say, so this is, this region is B equals heads, A equals tails. So I know C equals true here. And I know C equals false here, or C equals true here. So let's say, what's the probability of A given C? Given that I know that I get a heads and a tails in my two flips, I don't know what the second flip is, but I'm interested in what the probability of the first flip is. I don't know what the second flip is, so there's nothing pushing the probability that I'll get a heads or a tails anyway, or any direction. So it's still 50-50. But let's say so this is 1/2. It could either be heads or tails. Let's say that the probability that A equals heads, so I'm abbreviating A as A equals heads. What's the probability that A equals heads given that B also equals heads and C equals true? Well, if you know that C equals true, or you assume C equals true, either way, you know that there's one of each. And if you assume B equals heads, then A can never be heads in that universe. So I've restricted the universe to the following case. With this assumption. Or not this assumption, this given. B equals heads, C equals true. And so now, I know this is 0. So the probability of A given C and the probability of A given B and C are different. They're not equal. And that means that when conditioned on C, A and B are not independent. Because of C, when I know B, I get information about A and the other way around. Again, more formally, A and B are conditionally independent given C if, and only if, emphasis on the if and only if, the probability of A given B and C is equal to the probability of A given C. What does this mean? It means that when I know the conditional independence means that when I condition on this event, when I condition on this event in particular, A and B still do not inform each other, or knowledge of B does not give me information about A and the other way around. So had C been what is the value of the third flip, then given the third flip, A and B would still not give me information about one or the other. So they would be conditionally independent given C. I could have conditionally independent given some other variable. So they could be conditionally independent for one variable but not for another variable. And also, if A and B are independent, in the coin, allow me to gather my fluency back. So in the first example, A and B were completely independent, but in this new example, without changing anything about A and B, just adding a new variable, A and B were conditionally not independent anymore. So being independent normally doesn't guarantee that you will be conditionally independent, and being conditionally independent doesn't mean that you won't be independent when you don't condition on anything. And it has the same implication as earlier. The probability that A and B given C, or the probability of A and B given C is equal to the probability of A given C times the probability of B given C. And why this follows a similar derivation as earlier, because I could rewrite this as the chain rule. This would be the middle step. So I use the chain rule to condition on the probability of the event B and C, and then I multiply that by the probability of B given C. B given C doesn't change, but the probability of A given B and C then turns into the probability of A given C because of conditional independence. Okay, that's it for conditional independence. This is I sigh because it's I know it's rapid fire. I hope that you're able to keep up, and I take solace in the fact that this is recorded, so you can go back, rewatch, make it slower, make it faster if I'm not fast enough. I won't try to go faster because I'm at the limit. I'm hitting the limit of how fast I can physically go in terms of delivering material. All in the interest of not having a 2 hour long recitation. Okay. So let's talk about number of parameters. By number of parameters, we mean these probability tables have to be stored somewhere. If we're dealing with them on a computer, you have the probability of A, the probability of B, the probability of A and B. All of that needs to be stored somewhere. And often you don't need to store the entire matrix of numbers. You can store a few key points, what we're referring to as parameters, and that'll give you the information to cover the entire probability table. And I'll show you here. So let's say A and B are Boolean. So A can either be true or false. B can also only be true or false. And they are not independent, which means knowledge of one informs the other. And I can't simply say, well, I need a particular value for each of these. So the probability of A being true and B being true is one value. True and false is another value. False and true is the third value. And the fourth value, now I'm going to use the exhaustion principle that I mentioned earlier, where if I sum P1, P2, P3, and P4, I get 1.0. So I can simply say 1 minus P1 plus P2 plus P3. That's equal to P4, right? Because they all sum to 1. And what this means is that I need 3 parameters to store this probability table. And by probability table, I mean the P of the probability of A and B. I need 3 because I can then just take those 3 numbers and do 1 minus the sum of them, and I get the fourth one. So nothing too special, 3 instead of 4, but it adds up. But what if A and B are independent? True, true, false, false, as I did earlier. True, false, true, false. And now the probability of A being true, that's P1. And remember, exhaustion. So the probability that A is true plus the probability that B is true, the probability that A is false, so that's both sides of the universe around A, then that's 1.0. So I could just say 1 minus P1 is a probability that A is false, because if it's not true, it's false. And again, 1 minus P1, that's the probability that A is false. Now B is P2, 1 minus P2, P2, 1 minus P2. And now remember the implication from earlier about independence, that if A and B are independent, one of the implications of that is that the probability of A and B is equal to the probability of A times the probability of B. So P1 times P2, P1 times 1 minus P2, 1 minus P1, P2, 1 minus P1, 1 minus P2. So in reality, if they're independent, I just need two parameters. Okay, so you would think, big deal. I went from 3 parameters to 2 parameters. That's not amazing as far as storage on a computer. But let's write it out in terms of equations, because there is a way of writing an equation for this, or calculating the number of parameters. So if A and B are not independent, the number of parameters is equal to the product from I to n of the number of values in variable I. Let me just write var I to make it clear. Var I minus 1. So I'm going to take each variable in the universe. I'm going to take the entire range of the values that variable can take, and I'm going to multiply by that quantity. I'm multiplying by all of them. So that number can explode very, very quickly. As in, by explode, I mean it could get very large very quickly. Now, if they are independent, it's a drastic reduction in the number of parameters. Instead of a product, I get a sum outright, and that puny little minus 1 minus di well, now it's inside the summation. Which, okay, it's a minus 1, but we're subtracting 1 across all the sums, or across all the variables over which we're summing. And in the other one, we do this massive multiplication of a lot of values, and then at the very end, we subtract 1. So the impact of the minus 1 is greater, and obviously not even the importance of the minus 1 is eclipsed by the difference between having a summation versus a product. So if to make it more concrete or more relevant to the example on the previous slide, if A and B are Boolean, the number would be 2 to the n minus 1, as in the number of parameters, and if they're not independent. If they are independent, and they are Boolean, the number of parameters is n. A drastic, that's where it really lets itself show. To the n minus 1 parameters, suddenly down to n parameters just because they are independent. So now we're going to start talking about Bayes nets. And, whoops. This is, now that this is putting together, or starting to put together the assumptions that, or not the assumptions, the concepts that we discussed in the probability crash course. It was a lot of material. I recommend, if that was hard, going through the probability crash course again, perhaps working on your exercise, through some exercises on your own, making sure that you understand the concept of the space, conditional independence, marginal independence, marginal probability, joint, etc. But I'll proceed with Bayes nets. So a Bayes net is a directed acyclic graph and that graph represents I'm going to write the independence assumption. We refer to this as well as the naive Bayes assumption. I'm also going to just write it here, naive Bayes assumption. And now what is that assumption? I'm going to make this a gold star because if I want you to take something away from this video, or from this recitation, it is this concept, the naive Bayes assumption. So each variable in the Bayes net, or in a Bayes net, this is where the concepts start coming into play, conditionally independent of its non-descendants given its parents. This is the gold star idea. Make sure you understand what it means. I'm going to go through just a brief example with a Bayes net here. Okay, so the variable of interest here is f. And as this is a repeat of the naive Bayes assumption, f given its non-descendants and its parents is conditionally independent of its non-descendants, and if we apply the definition of conditional independence, we can say it equals f given just its parents. We can eliminate the non-descendants from its givens. More concretely, let's say I have the non-descendants of f. This is equal to a, b, c, d, e, and the parents. The parents of f are just d. So the probability of f given a, b, c, d, and e then turns into just the probability of f given d. And that is the naive Bayes assumption in its in simplified form. Now, one of the last topics, the second to last topic in reality, that I want to talk about is d-separation. And d-separation, what it involves is how do you determine independence of two variables? You could just prove that the probability of some variable given the other is equal to the probability of the first variable in the first place. That's how you prove mathematically independence or mathematical independence. We can refer to those in different ways here in 6034. But there's another way, and we refer to this as structural independence. There's a way for you to use the Bayes net in such a way that will allow you to determine whether two variables are conditionally independent given another set of variables. And the method that we use is d-separation. In the example prompt here, I'm asking you, what are A and B conditionally independent of D and F? So given D and F, are A and B independent? And I've rewritten it here as, is the probability of A given B, D, and F equal to the probability of A given D and F? That's the definition of conditional independence. I recommend that you go to the previous slides and review it if you're having a hard time remembering the definition. Allow me to get some water because my throat is getting a little bit dry. Okay. This is a lot. I'm going to work through the example with you and visually too with the Bayes network. But roughly said, I'm going to briefly go through them and then actually go through the diagram. The first step in d-separation is to draw an ancestral graph, which means you take the variables and the givens, and you draw all their ancestors up. We don't include descendants. And then you go through the graph. This is step number 2, and any two variables that share a child, it's directed, so they just their arrows point toward a common node. Those are parents of the same child, so you draw an edge between them. You can draw an undirected edge, because the next step is to disorient the graph. And what it means is you make the graph completely undirected, you cross off the arrows, and then you delete the given variables. You erase them and all their connections, and then you can read the answer off the graph. Okay, and by reading off, this is where I briefly mentioned mathematical independence versus structural independence. If there's a path between the two variables, this is referring to the fifth step, sorry. If there is a path connecting the two variables that you wanted to investigate at the beginning of d-separation, then they are structurally dependent. If they are completely disconnected, they are structurally independent. The asterisk happens because the structure of the Bayes net says that these two variables are dependent, but if you mathematically go about it, there could be a case where two structurally dependent variables mathematically turn out to be independent. As in, for example, the probability of A given B is equal to the probability of A, even though the Bayes net says otherwise. It's rare. We won't. I won't say we won't give you a problem where that wouldn't happen in 6034, but it's a rare case, and it's not 100% guarantee, but you can take it to mean that. You can take it to mean generally that if they are structurally not independent, then they're very likely not mathematically independent either. But if they are structurally independent, then they will also be mathematically independent. That is a guarantee. Structural independence means they are also mathematically independent. So to go through the examples formally, the first step was to draw the ancestral graph. So I am interested in deleting or drawing the variables, their givens, and any ancestors. Briefly looking at the variables, I see the lowest one down the chain is f. So I know I'm drawing everything up to f. This is not an ancestor to anything that is of interest to us, which means that's going to be deleted. So this is the result of step number 1, drawing an ancestral graph. Okay. So what I said for step number 2 was I need to find all nodes that have a common child, all pairs of parent nodes or sets of parent nodes, and I draw an edge between them to link them, like so. So this is the result of linking parent nodes. Now the third step is to disorient the graph, which means I'm going to be deleting all of these. So now my graph is undirected. Now finally, I delete the givens and their edges. I realized I jumped to it a little bit early. So here I have D and F, those are my givens, and now they're gone. And then the last step is to read the graph. And now, repeating what I said earlier, there is a path or there's a direct connection between A and B in this. So my conclusion then, because A and B are connected, is that A is not independent of B given D and F. And here I apply the disclaimer: A and B are structurally dependent, but may still be mathematically independent. Again, it's rare that it happens, but it's a possibility. And I think it's important to keep it in mind. Okay. The last concept, that's the end of D-separation. The very, very last concept that I want to cover today is explaining away. And explaining away is I want to phrase it in a very intuitive way because to some extent it can become difficult to grasp as a concept. It seems my notes are experimenting or experiencing technical difficulties, so we're freestyling the end of this recitation. So let's consider two different ailments that may or may not affect me. So let's say the variable A is for when A is true, it means I have a broken arm. And when F is true, I have the flu. Thankfully, I'm happy to report that as of the time of recording, both of those are false. But for the sake of the recitation and the example, let's assume, those could be true or could be false. Oh, my notes are back. How convenient. We're not freestyling as much anymore. So I either have a broken arm or I don't. I have the flu or I don't. And those are random ailments. It could have been anything. So it's not hard to see that they're fairly independent. As in, whether I broke my arm or not wouldn't tell you whether I have the flu, or the other way around. If I have the flu, it doesn't inform you of whether my arm is broken or not. And they don't really affect the probabilities of each other. So that's the background. Now let's say we're not talking in general. We're talking about seeing me in the emergency room. So you see me in the emergency room. Right? That's the given. And now you think, what is the probability that Hector broke his arm? Well, it's definitely higher, right, than the probability that you saw me on the street and that I broke my arm, or that I had my arm broken. And it's the same thing the other way around. If you see me in the emergency room, the probability that I have the flu is higher than if you saw me on the street, and as in out and about, and I had the flu. So far, so good, hopefully. So the important step here is that given this information, the probability of this variable is now higher. The probability of A is higher, the probability of F is higher given E. But now, let's say you see me in the emergency room. And you know I have the flu. What is the probability of A? Or the other way around. Let's say you see me in the emergency room and you see I have a cast on my arm. What is the probability of F in that case? What is the probability that I have the flu? And that's the big punchline of explaining away. The probability that I have a broken arm, given that I'm in the emergency room, or that you see me in the emergency room, and that I have the flu, is actually less than the probability that I have a broken arm and that you see me in the emergency room. And the same goes the other way. The probability that I have the flu, given that I'm in the emergency room and you know that I have a broken arm, is less than the probability that I have the flu and that you see me on the emergency room. So that is explaining away. It's these two events, they're independent, but then this third event makes the individual event, so the original event A, the individual event F, they become more likely given the third event. So given this child, when this child is true, the parents, in a Boolean example, if this child being true gives you more information, gives you information about the parents being true, or it makes it more likely that the parents are true in this Boolean example. In a less Boolean specific example, information about the child gives you information about the parents. But when you don't know, but when you have information about the child and one of the parents, it explains away information from the other parent. And we see that the explaining away happens here, where me being in the emergency room and you knowing that I have the flu that's the explaining away step. It's, oh, I'm in the emergency room because I have the flu, therefore the probability that I have a broken arm is much lower than if you only knew that I'm just in the emergency room and you didn't know whether I had the flu. So once the child acquires this true value, both of the parents become more likely to be true. But once the child and one of the parents is true, in the setup at the very least, the other parent becomes much, much less likely to be true. And that's the intuitive grasp of explaining away. There are other courses that explain it much, much further, but I wanted to give you an intuition for what it is and what it means. So I think this has been so far the longest recitation that I've recorded. I know it was dense. It had a lot of material. I think it's been the most theory-packed recitation so far. I hope that those of you that have some probability background, that this served as a review, that maybe it introduced some new intuitive way of looking at these different probabilities. If you're new to probability, the purpose was to give you a basic intuition of what it is. Please do not go and take a probability course based on what you know from this recitation. It's only a crash course meant to sample probability and to introduce you to the concepts that we're now using in Bayes nets. You saw it with the naive Bayes assumption, where we started playing with conditional independence and givens and ancestors and whatnot. That's part of the Bayes. For the next recitation, we're going to go into more detail in Bayes, not as much probability review, and I hope to see you next time.